Okay, hi everyone. I'm Shang Lin. So this is my DSA final project presentation. So my topic is implementation and analysis of Merkle trees in blockchain systems. So first of all, we need to understand the blockchain block. What is in the block, right? So a block consists of the two main parts. It's called a block headers and the transaction list. So the block header contains several metadata such as a previous block hash, which link the block together, and the Merkle root, which summarize all transactions in the block. And we also need to know the obvious information like the timestamp and the difficulty target and the notch for proof of work. So the other part is that the transaction list. It includes all the transactions within the block, and starting with the Coinbase transaction that rewards the miner. So we were focusing on uh, the the Merkle tree and the Merkle rule, and we will discuss the usage and the benefits of that. So we need to be curious that why do we need a Merkle tree? Imagine a block with the thousands of transactions. So without the Merkle tree, verifying the single transaction will require downloading and checking on all transactions in the block. So this is very not efficient, right? So the Merkle tree organizes transaction into a tree structure and allowing verification with only a small portion of the data, such as the Merkle roots and a few hash values, and making the process much faster and more storage efficient. So we also want to know what is the items inside the Merkle tree. So how it works and how it looks like. So in the left plot, we can see the Merkle tree organize the transaction into a hierarchical structures. It was like each transaction, T1 to T10, each transaction is hashed to create the leaf node. And these leaf nodes are paired, hashed together, and all the process continue up the tree until the single hash. So it calls the Merkle root. And the Merkle root summarizes all transaction and is stored in the block header. So if the transaction like T1 is a change and it affects the whole tree and update the root hash and ensuring the data integrity. So we also need to know the hashing function within the Merkle tree. It calls the SHA-256. It's a widely used cryptographic hash function, and particularly in blockchain system like Bitcoin. So it has three key properties. As I first is the fixed length outputs. So the outputs always will be the 256 bits regardless of input size. And the second one is collision resistance. So it's computationally infeasible to find two inputs with the same hash. So the third one is the one-way function. It's almost impossible to reverse engineer the original data from the hash. So this is the whole reason why we want to use the SHA-256. So for example, the word hello hash with this algorithm will produce the whole string is there, right? And if we will change the hello, big hello to small hello, it will create a completely different hash. So this is how the SHA-256 works. And we also need to know how Merkle tree save this space. So it was like the Merkle tree let us remove all transactions, right? So once transactions are buried under many blocks, this data can be deleted. So we will save the storage, but the Merkle rules stay in the block header. So if we want to verify a single transaction, only a few branches of the Merkle tree are needed, and saving the storage while still proving the transaction exists. So this is like the next part is my Python demo. So I follow the several pattern. So one of that is transaction as leaf node. The second one is I need to follow the hierarchical structure, and the third one is the Merkle rules should be generate. So this code is and this code demonstrates how to implement the Merkle tree in Python. So the first of all, we need initialization. So the leaf of the Merkle tree are created by hashing the input data, right? So uh, a, a build tree method construct the tree from the leaf to the root. And the second part is the hashing function. Each piece of data is hashed using the SHA-256 to ensure the whole security and data integrity. So the second one, we build in the tree. We use the build tree method, and starting from these leaves, a pair of the hashing are combined and together and hash again to form the parent nodes, and this continues until the root hash is formed. So if it's like we need to be aware that the odd nodes situation, the odd nodes are duplicate to ensure that the old level are complete. So this section, I want to introduce the visualization part, but I think the time is not very sufficient, so maybe I will skip to jump into the next slide. So this slide explains the transaction verification in Merkle tree. So to verify the transaction is hash and the corresponding proofs like the sibling hash are used to reconstruct the Merkle root. So if the reconstructed root match the stored Merkle root, the transaction is valid, right? So it is the example I put it in my algorithm. So it shows that it's my final output if the Merkle root is generated, and it is the plot. Actually, it's not very perfect, and the transaction add is valid. So actually, the Merkle trees are very widely used in blockchain systems like Bitcoin, everyone knows, to ensure that the transaction integrity and scalability, right? So they are also applied in distributed storage system for efficient data verification. So for instance, the simplified payment verification allows lightweight nodes to verify transaction without downloading the entire blockchain. So actually, during this period of the research in the Merkle tree, I really like to send to the Merkle tree structure in and it is used in the world and then in several places. It is very useful. So this is my final presentation. Thank you for your listening.